committee, I should say, of people, volunteers, put evening events on, evening lectures on. Hopefully are interesting to you. You're here, so that's a good start. Open to everyone. Anyone who wants to attend to any of these lectures, completely, you don't have to be a member of the IMechE or anything like that. Bring your friends along, encourage them to come along, that'd be great. I'm really keen to understand a little bit more about what we can do for you, make sure we're providing the events and the lectures that are of interest to you. So very much welcome any feedback. Come and call me or one of the other committee members after this. We'd love to know your views on that. Just before we start then, a little bit of housekeeping. We're not expecting any fire alarms or anything like that. Toby is our host in terms of the building today. If there is a problem or alarm, the fire exits are pretty much back out the way you came, I believe, by the lift. Is that correct?
Yeah.
Yeah. And we can follow Toby. He will guide us to safety. Just looking forward before we start, our next lecture is on the 19th of November, and that's with Ian Rawlings, who's head of vehicles at London Underground. He's going to talk to us about some of the work that he does with some of the other metros in Europe and possibly around the world, get some contrasting views. That should be really interesting too. I'm looking forward to that one. Without any further ado, we will move on to the lecture. I'd like to welcome Andrew Brice, who is, I get it right, hopefully track engineering manager at London Underground, and has had a lot to do with the new trains, which hopefully you're all aware of, the Piccadilly line trains that will be hopefully shortly introduced. I'm really looking forward to it. I know there's been a lot of interesting challenges with integration with these trains. I'm sure you'll touch on it. They're very novel, these trains, in terms of their configuration, in terms of some carriages having no wheels at all. And I'm sure we'll learn a little bit about the track interface, PTI, gauging and power and all of those sorts of things. So if you could join me in welcoming Andrew. Thank you.
Echo. Echo.
Okay. Get going. Yep. So, good evening, everyone. Thank you for inviting me today. Obviously, everybody's aware of the new trains on London Underground. New trains have just been brought into service on Dockland-side Railway. If you like, the next 45 minutes or so will be highlighting some of the issues that track engineers have when we have new fleets of trains. New fleets of trains are generally a good thing. And we will actually, as well as touching on some of the issues with 24 tube stock, we will pick up on S stock and 09 stock as we go through. Like all things with the Underground, well, where did it begin? If we go back to something like the 1860s, that's what the railway used to look like, very different to today. We don't have steam anymore. We certainly don't have that much room in our tunnels anymore, and we certainly operate at a faster speed than we see in that day. There we are as an example of a circle line platform for the time. And, as much as, the picture looks quite interesting of the time for it, from the viewpoint of a track engineer, we do have to remember we're putting new trains on infrastructure that dates back to the days of our Victorians. They certainly didn't construct and build things to what we might recognise as modern codes of today, and therefore that creates in itself a set of issues that we'll run through today and with solutions that we've built here. So in terms of where we're going to go through, we're going to start by talking about ride quality, talking about structured gauging, platform assessment, train arrestors, conductor rail, and what I loosely called others. It's not to demean the others, but we'll spend more time on items 1 to 5. So generally speaking, in our experience with sort of designing a train, obviously one of the things that we're interested in is looking at the movement of the vehicle within the specified kinematic limit. We know that's a trade-off between the space that is available, the way the track is maintained, and the suspension of the vehicle. What we don't want to have is a track that's so difficult to maintain, we can't get out there and maintain it. Equally, we don't want to have a situation where we have a vehicle that moves so much in response to the track that we can't predict where its movement is and it doesn't keep within the kinematic limit going forward. Particularly for London Underground, access is at a premium. There's next to no places where you can store things. So in essence, the tools, equipment we take down at the start of engineering hours, at the end of engineering hours, and take them back again. Logistics is a major issue from the viewpoint of the track engineer. And therefore, getting the right balance between the two is key for this. When we did an exercise for SSOC with what was then Bombardier, we looked at track recording vehicle data for the entire district line. We didn't tell them what the age and what the type of track form for the data was. They then used the TRV data with Vampire to model the resultant ride quality. What came from that was that they identified that there was an issue with the trains running faster than 70 kilometers an hour, where the set ride quality parameters were exceeded. This we translated through into a ballast memory issue to do with the way that the track used to go down in 18-meter panels, which were joined together. The pleasing thing was, though, that on the one section of the district line where it did meet the ride quality parameters up to 100 kilometers an hour, that coincided where we renewed the track. So from the viewpoint of the track engineer, immediate validation that we were doing the right thing from the viewpoint of the rolling stock engineer and standards. We then repeated that for sections of the Metropolitan line where we carried out track renewals, and there was a good correlation between the two. So if you like, independent validation of why we were renewing track, and we were renewing track to the right standard, which is always pleasing. In terms of structure gauging, I apologise now if those of you who've seen this type of slide, but very much on the underground, we have something called the kinematic limit. The kinematic limit is independent of speed, or shall we say, up to 100 kilometers an hour. That is the particular line speed. The idea is the train stays inside the blue, and the infrastructure stays outside of the structure profile. Now, for a lot of undergrounds, compared to the mainline railway, we tend to work with smaller margins than you might find. So typically, for the subsurface railway, we look to have 50 millimeters between the kinematic limit and the structure profile. So that means that when a train runs, it should have about that much between the two. So, when we start the issues with new fleets, first things we say to ourselves is, well, okay, we've got standards, we have a set structure profile. Structure profile will vary between where we have tube trains running and where subsurface or surface trains running. But the first question is, are we compliant? Because the best will in the world, at the age of the infrastructure on LU, invariably there's somewhere where we're not compliant. We then say to ourselves, if we go with the kinematic limit as specified in standards, what will a concept vehicle give us in terms of maximum capacity, i.e. how many people we can carry, compared to the need for safe, adequate clearances? Having completed questions 1 and 2, we then go and talk to our stakeholders and say, what remedial works do we need to do? So, for instance, when we were looking at SSOC, we identified that there was approximately 10 kilometres of the circle line that would need to be rebuilt. Now, that doesn't pass the value for money test, and it's certainly not practical, and it certainly wouldn't meet timescales. We then go to platforms and we say to ourselves, you know, what are our existing heights? Are we generally compliant to standards? Are we high or are we low? And then from there, with the concept train, what does that mean in terms of what we would need to do? You know, how can we optimize the platform train interface as much as we possibly can based on the existing infrastructure? If we need to make a change, okay, what are those changes? What's involved with doing that work? So if we move on, we've also had a bit of a technology boost during the last 20 years. So if you look from these photographs here, prior to 2004, it was very much, you know, conventional wooden gauges, you know, that have been used for the previous 100-odd years of use on London Underground. They are good in the sense that they give you an immediate visual image of what's going on. And relatively speaking, you can identify, you know, what is the offending part of the infrastructure. But it's very labour intensive. As you can see from the subsurface frame on the left-hand side there, you know, typically you need 3 or 4 people to move the gauge as you go along the track. And it's also quite difficult to gauge readings around the profile. Tube is a little bit easier to work with, say, again, a good visual image, but, you know, once you've taken your measurements, the iterative process is quite difficult. So following on then from post-2004, as much as the railway industry is now from the viewpoint of track, both on mainline and on TfL, we all tend to use the type of equipment you see here, where you've got a scanner based on a trolley that runs on rails. The issue that you got, particularly from an underground perspective, is that as you push the trolley through, you actually generate a helix. And the distance between the helix is key for the type of clearances you've got. So unlike, for instance, Network Rail, who have their own train-based gauging system, which runs through the network, because they, generally speaking, have greater clearances than are on the underground, that is an appropriate technique for them. If you try doing the same thing on London Underground, you'd probably miss most of your clearance infringement. And therefore, there needs to be something done in greater detail. And, you know, we've been working with companies like Leica and others to evolve this equipment and the post-processing afterwards. So from the scan, what we end up with is a series of sections. Against those sections, we plot on the vehicle profile, allowing for curvature and allowing for cants. And like all these things, you know, processing the survey data has its own checks and balances, because if you're not careful and you end up joining the dots together on the profiles you collected, you can create false positives where effectively, you know, the survey and the way you process it, telling you the top half of the train is clashing with the structure. Well, you know from the operating service that's not the case. So you then have to go back and check your post-processing. It can catch people out. You know, the surveyors on Crossrail did that a number of times as part of driving the tunnels, and we had to step in, say, by the way, you made a mistake, need to correct as you go through. From that, what we then can end up doing is saying to ourselves, well, you know, if our infrastructure is quite difficult to modify, what we can do is put together a composite infrastructure outline and then say to ourselves, well, what does that mean in terms of our kinematic, and therefore do we make a modification to kinematic? Obviously, the trade-off is if we have a smaller kinematic, that impacts on the train builder, but it depends where that is. And that's something that we did on this example here for SDOC back in the heady days of August 2004. What was actually also quite interesting for our civil colleagues is that we identified that the previously thought of horseshoe-shaped tunnels actually have flattened over a period of time, and that there was a clash around the cant rail level here that was very difficult to resolve from the viewpoint of the civil assets. So we took the decision that we would make the kinematic limit smaller in that area, but in terms of the usable space passengers, that was maintained. That would seem to be a reasonable trade-off. In terms of platform assessments, this is quite a busy slide, but if you like, what it brings in is that there is a number of things that have each got their own tolerance. So, for instance, track itself is maintained to a line and level. That has maintenance tolerances. The train itself has tolerances in terms of how it's maintained and how it responds, but also in terms of how it's built. And we did have a windy Friday afternoon in Neasden when we did measure across the train, that it was a different dimension to that we were expecting. But Bombardier assured us that's okay, and we worked on. Equally, platform nosing up here is maintained. They do replacements, but they won't necessarily check it back against the optimum track position. And therefore, you can start to lose that relationship between the two. So, within those three, there are tolerances. Gauging by its very nature is very conservative. If you're not careful, the build-up of tolerances can work against you. So, because we were trying to optimize the space between the train and the nosing, to try and bring it down as small as possible for things. Our original design concept, we assumed a certain offset for the design. What we found was to consistently achieve less than 75 millimeters, 75 millimeters being the widest dimension allowed under the Railway Vehicle Accessibility Regs, RAVA for short, meant that from a design position, we had to say, right, our design should give us 64 millimeters between the two, so that we had margin as we go through. But as you can see on the slide here, we've established a number of the tolerances that we've found in reality as well as we had in standards. So the upshot is that whilst engineers like standards to work to, during our experience with bringing new trains onto the underground, there are a number of times we have to go back in and challenge our thinking about why are we using that standard figure, and is it appropriate as you go through, and you end up with an iterative situation. So in terms of clearances at platforms, straight level track, really easy to work out. Fortunately, London Underground doesn't like straight level platforms. You then move on. You then have a situation where the track is canted away from the platform. That's great from the viewpoint of the ends of each individual carriage, because of end throw, get closer to the platform. But if you have doors towards the centre of a car, they move further away from the platform, so therefore your gap gets worse. Equally, if you go the other way, centre of the train and the doors closest to the centre of a car are closest in terms of your distance between train and platform. So you then end up saying to yourself, well, you know, what have I got in terms of combinations of curvature and applied can? And particularly from the viewpoint of complying with the RVAR regs, where do I end up electing to choose the doorways that I'm declaring that will be RVAR compliant for as much as the particular line that you're working on? Again, you know, there's this whole iterative process to go through. And the other thing that we found we have to take into account is that, you know, whilst you're looking at level access for a train that's at rest, trains obviously brake into their stop position and then accelerate from their brake position. So for London Underground trains, a train as it comes to the top of ramp in direction of running, front of the train is doing approximately 35 miles an hour. Obviously, when the back of the train gets to the top of ramp, it's at 0 because you braked. And then for the back of the train as it's leaving the platform, obviously the front is at 0, but the back is doing 35 miles an hour. So if you then add that speed differential and what it does to the vehicle in terms of where the vehicle sits, you've got a two-stage problem. You've got the problem of minimizing the gap for a train at rest, while also having sufficiently safe clearance for a train that's moving. And as you can see, as we've put in here, you know, train at rest sits in this position, but with movement, it can come across and get very close and hit obstruction. One of the things that we ended up pioneering for Deep Tube was platform humps, such that at the RVAR nominated doorways, in this case it's for 09 stock on the Victoria line, that we would have steps and gaps at the nominated doorways where the offset was less than 75 millimeters and the vertical step was plus or minus 50. These have worked quite well, not without issue. You know, so for instance, you know, if you look around, you know, the platform furniture, you've got manholes sitting in the surface of the platform. Has the track been renewed? Is the track is optimum alignment? Because you end up having to optimize the alignment, could well impact on here. Obviously, we need to consider the slope coming off at the access egress points to a platform. Victoria line is relatively easy to work with. You start taking that onto some of the older lines as they're currently finding on the Piccadilly line at the moment. It really is a magnitude of problem of difference as you go through. Like all things, you know, when we were told, oh yeah, they're fitting platform humps, what should the offset be? You went, oh, that's a good question. We haven't done that before, have we? So again, you know, we did some trials and tests out at Greenford of all places to try and identify what that optimum platform height and offset was as we went through. Because as I say, it's quite easy to say platform hump, but when you say how far should it be off, it is a different thing. This is an example of a well-known platform on the undergrounds, and you can see the issue about curvature as you go through. So here, as you can see, we're sitting on the inside of the curve. So at the end of the carriage, we're really tight for space as you go through. But because of the curvature and the way that the train sits on the track, we end up having a lot wider gap at the particular doorways as you go through. And as I say, that's the joy of the infrastructure, the age of the underground. But it is a very real problem, because obviously what we don't want is we don't want people falling down the gap with incidents that you get there. So, there's been a lot of head scratching and thinking about what we can do to try and sort those sort of problems out. So in terms of benefits and weaknesses, it's great from the viewpoint of level access, no or a small vertical step. I know there is a debate about what should that small vertical step be, but I'm not going to touch on that now. But if you think about going to more modern metros with the way that you don't worry too much about walking in and out. For instance, Stockland's Light Railway is an example of where they've got that pretty good. In terms of delivering RVAR, straight track helps. I've said on the underground we don't particularly do straight track. What we found though is where the curvature is generally speaking flatter than 650 meters, we can achieve RVAR compliance, with the caveats that your track alignment and fixity are good, and everything is in tolerance. It's easier for mobility impaired persons to get on and off. I believe there is a YouTube video showing one of the wheelchair access groups going on and off an S-sock at Harrow on the Hill, and do it remarkably easily. Obviously, we talk about wheelchair users, but equally looking at people with buggies with young children, what have you, that's a concern. So in terms of the weaknesses, if you're not careful, particularly during transition, that's something we will touch on generally speaking, but the one new train in, one train out means you've got this mix of fleets, which therefore can create issues when you go through, and that you can actually end up sometimes making the horizontal gaps worse during transition until you've got your new fleet in place. And as I say, difficulty in achieving RVAR compliant on tight curves or poorly aligned track go through. So again, we talk about railways as a system. As track engineers, we're very aware of that system, what needs to be involved with change. And then, obviously where you go on, one of the key things with it is to make sure that the track is datum, so the maintainer know what's involved. We have developed gauges, as you can see here, to demonstrate that we meet the requirements for the gap being no larger than 75 mil, where it's at an RVAR nominated space. Again, we're doing that type of work. The gauge was also developed from the viewpoint of human factors. It's continually having to bend down. And in terms of testing for doors, because the stopping tolerance has plus or minus a meter, what you end up doing is taking 9 sets of readings. So you have both sides of the door and the middle of the door at 0 tolerance. You then repeat those 3 readings at plus 1 meter and minus 1 meter from the stopping tolerance as you go through. As you can see in there as well, also looking at how tactile strips are put in place and go through is another key component for these things. And then where you can't achieve the gaps, then saying, right, what are we doing in terms of warning to the travelling public, in terms of audible announcement or markings on the platform. So, again, often the track engineer is there chasing the millimeters. what's involved. There's nothing more frustrating when the test team go out, measure the gap, and it's 77 millimeters, and you go, need to go back again. It's quite frustrating. One of the other things that we talk about is, are we leaving things in a tolerable position from a risk perspective? And particularly with gauging, it's difficult to get there because inherently gauging engineering is conservative. One of the things we have been doing is we have been working with companies like D-Gauge on using probabilistic techniques to see how that helps us manage the risk. And I know that works continuing on the mainline network. And we continue to work with them on our fleets as we go through. And therefore, particularly from the viewpoint of curb track, sometimes we will use it to say where we can take an existing gap from 160 millimeters down to 120 millimeters. So we know we don't compete with RVAR, but from the viewpoint of improving the gap and therefore lowering the risk, if we can get a gain using probabilistic techniques, that's something that we will actively look to do. The other thing that we often look at is train arrestors, and we end up saying to ourselves, right, okay, well, where is the contact points on the existing train? What we don't want to do is we don't want to introduce a new train. First time it ends up engaging with the train arrestor right off the driver's cab. That's a complete train we have to take out of service. So we look to model the interface zones. Invariably, you will be, you'll have at least 2 train types. And you will also need to look at engineers' trains. When we were looking at the Uxbridge branch, we had the joy of Piccadilly line trains, 73 tube stock. I had to redo the exercise for 24 tube stock as well as at the time we still had A stock in service, as well as bringing in S stock and engineers' vehicles. So we had 5 train types that we've had to work with on the Uxbridge branch, which, got the head scratching a little bit as you go through for it. Also, what we found was that the design of the train arrestors, or call them buffer stops, was something that had been derived empirically over the previous 80 odd years. There was no design calculations. There was no way of understanding factors of safety. The bolts that were specified for it, nobody could find out why they specified those bolts, why they specified those gusset plates. So consequently, we ended up in a situation where we really had to go back to first principles. And for train arrestors, we wrote something called a principles paper. And the principles paper pulled in a whole load of inputs from rolling stock, track, signalling, power. We even spoke to the escalators team to try and work out what was the mass of an average person. Because believe it or not, depending on which publications you read, the mass of an average person does vary. Why do you consider that? Well, one of the things you have to allow for is a crush-laden train. And therefore, if you can't agree on the mass of an average person, your train's carrying 800 people, that's going to make quite a bit of difference to the sums as you go through. As well as looking at the front face for it for these things, you also need to consider what's going on in terms of it vertically, where the coupler is, and so on through for these things. So typically, when we talk about upgrading train arrestors from a track perspective, I've touched on train arrestors. We also need to look to see, does the existing conductor rail layout fit for purpose? Does it go far enough? Because what we don't want, particularly at terminals, sidings, depots, is to find that the front shoes are not on power, and therefore, the train might sit down and not go. You have to consider conductor rails. Are there signals that need to be relocated? The sight lines on new trains are very different to old trains. Invariably, it means the signals need to be put further back in a different position. That's great in a number of our open areas. If you're in an enclosed tube tunnel, relocating signals in that area is really quite difficult. We also need to consider where insulated rail joints are, where train stops are, safe operation of trains. We also need to consider operational signals, stop marks. There was quite a discussion over stop marks for the operators in terms of what was permitted for them. Could they see the diamonds that were sitting in the forefoot of the track? No, that's not good enough for the new trains. Therefore, we need a series of stopping chevrons. You then have to work out how you locate the stopping chevrons. Driver access platforms are a particular feature of the Piccadilly line, pleasingly only the Piccadilly line, but they come with their own issues that we're working our way through. Extension or relocations of walking routes. Rightly or wrongly, in our experience as track engineers, new trains always come longer than the old ones. And I dare say that there are others far more informed than I will tell me why they have to be longer. But it does therefore mean that you need to look at where your walkways are relative to the stopping point and say, do I have to relocate the walking routes? There's obviously a trade union implication for that. That impacts on the drivers and their walking time. Also, if you're migrating between fleets, and particularly we found with the difference between a C stock, which is about 95 meters, compared to an S7, which is about 125, that created no end of issues about determining which was the end that both trains stopped at, and therefore where did you put your walkway. You've also got to think about the walking route in terms of the driver for testing trip cocks, if trip cocks are fitted on the new trains. Also, in addition, is looking at lighting. Is the existing lighting sufficient? Do you need to put new lighting in place? In which case, how do you run the new lighting? Is the power supply in place? Don't ever assume power supplies are in place. As railways, we always seem to be short of power. Civil engineer will get in on it as well, in terms of where there are drainage runs, catch pits. I almost lay money that wherever I want to put something new, there will be a catch pit there. And therefore you have to work through the impact of that. And then, you then start getting into other civils related works in terms of, what's the formation if you're going into a piece of railway that's not used at the moment? Do you have to do any stabilisation works to go through there? Are there pits that need to be filled in? And that's an example of some of the things that we find and we come across. So here we have a driver's access platform that they've put in place for an existing train. New trains are longer. What do we do with the driver's access platform? We put one here? Well, no, you can't, because you can't then get in. So, there's a whole issue there that needs to be worked through. What you'll notice from here is there's lots of green stuff, lots of dodgy looking sleepers, lots of worn out rail. Well, LU has had a policy of cascading rail sleepers from the main line into their depots. So consequently, it works fine. Start modifying the assets, and you then start to find you've got a number of series of issues. Here, the depot formation is set on ash. Now, ash, if you don't disturb it, generally speaking, it's all right. It's clogged, which is why you've got vegetation in it, but it tends to behave. If you then need to start moving sleepers around because you're moving your train stops or your conductor rail positions, or you're having to move your cables because you're changing your Conrail layout, Ash doesn't respond very well. Oh dear. What do I do? Oh yeah, I know. We've got this new thing called granite ballast that's used on the main line. Let's put some granite ballast in there. All right, okay. So we then reballast. Oh, we better do the sleepers. Oh yeah, we need to do the rails, don't we? Because we've got an obsolescence issue. How do I join the new rails to the old rails? Or more importantly, as one of my engineers said to me last year, where do I stop? You know, you have to think about being economic and viable as you go through. So, you know, there's quite a lot involved with seemingly with bringing these trains on. You know, this is an example of something that we've had out on the railway of what used to exist. Pleasingly, the track maintainer has painted the face, but both of those bars are completely the wrong height. So therefore, if a train were to engage, it would go straight through the middle, and this would go straight into the cab. So, you know, we don't need that. This one here, this is an example of station staff doing their bit to improve the environment for travelling passengers. As much as it's nice to see these plant pots, this is actually an old-fashioned type of drag arrestor. So the idea is, or the concept, that should a train overshoot and hit this here, the energy then pushing everything out of the way would then be dispensed and the train would come to a halt. Once the flower pots, no. Maybe there's special resistant flower pots. You know, who knows with these things. From the viewpoint of the track engineer, though, you know, it's a pain because there's rails under here. Where do you get to see the rails? You know? What happened to CDM when they put it in? Oh yeah, it didn't exist. So, you know, one of the jobs that we've had to do is we've had to strip all of this out. We've put completely new track underneath, and we've put a new modern friction arrestor in place. And that work has now been completed, if you know where to go on the north end of the Piccadilly line. This is an example of some of the issues that you have when you're inside a turnback siding, as is common on a number of London Underground lines. So as you can see from here, you know, you've got the existing bullhead rail, you're inside a cast iron tunnel. Someone's chucked some sand at the ends as a means of stopping the train should it miss the stop mark. And there's a nice bright red light there to tell the driver don't go to the sand as you go through. You know, doesn't really meet the needs of a modern railway as you go forward. So consequently, you then end up saying to yourself, right, okay, how do we upgrade? So again, there's a series of staging works where effectively we put in a temporary train arrestor, do the works in and around, and then once we've completed those works, we can then put a modern friction arrestor on there, because we all like friction arrestors, because it means if a train hits it, brings the train to a stop without breaking the train, and the train can carry on its service. As you go through, also you'll notice, you know, there's not masses of room in there. You remember my earlier comment about storage or lack of storage space. So again, with these, you can only ever get access in engineering hours. So effectively, they're locked by the railway during traffic hours. So again, thinking through the logistics, thinking through with what's involved is quite complicated and involved. That's our old friends, you know, the drag arrestor, and that's what a modern one looks like. You go through. Conductor rail shoe. Underground is a 4-rail system, positive and negative conductor rail. well as the running rails. We also have a fifth rail called the check rail. You go through. As you can see this arrangement here, obviously, power goes to the conductor rail, shoe picks up, power goes through to the train. Therefore, we need to have good conductivity between the shoe and the conductor rail, and the two need to overlap quite nicely. Again, new trains, they like more power, please. And that's due to their train wall systems. That's progress, fine. But we do need to get the power from somewhere. We also have regen braking with the trains, and that can be used to be more energy efficient, but the voltage can increase to 1,000 volts. So therefore, we have to look at the power infrastructure and say, in terms of the breakers that are in place, if the voltage is going to go up to 1,000 volts, you don't want them to trip the first time the first train goes into regen. So you then end up saying to yourself, well, you then need to look at your power infrastructure and say what needs to be changed, what needs to be increased. Now, one way of improving the reduction in voltage from the substation is to install something called composite conductor rail. And London Underground's been installing composite conductor rail now since the 1990s. It's a really effective way of reducing the power loss from the substation. It has its own vices, and from studies that we've done, we have assessed it as having a 75-year life. But equally, if you've got a wet tunnel, water falling off the conductor rail dramatically reduces the life of your asset. So again, the civil engineer has a key role to play. For new trains, we will carry out something called a gapping analysis, because not only the new trains are longer, the shoes picking up on the conductor rail are in a different place. So what you may well find is that a route that didn't gap for the old train could potentially gap for the new train. Sometimes it works the other way in our favour. But obviously, during interrunning of the old and new fleets, we have to cope for both situations going through. And as I say, we also have to check for other stocks that will be going over the infrastructure, because again, their shoes will be in a different position. So if you take the Uxbridge branch, when we were rolling out S stock, we had S8s, we had A stock. We also had 73 tube stocks to contend with as well. All three trains had their shoes in different places. So, there's quite an involved process that goes through in terms of understanding what is the rollout program, when does the rollout program take place. And that gives you an idea of some of the conductor rails that we've got available to us. As you can see from the top there, we haven't got a great deal of room to play with in the cast iron tunnels. And therefore, the height and width and cross-section area of the conductor rail makes a big difference to what we can and can't install. So, ideally, if we've got lots of space, we would like to go for something like this, what they call Section 7 composite conductor rail, which has the greater cross-section area. However, due to space, we sometimes have to go for a smaller section. And that in itself creates issues. So you then end up saying to yourself, you measure what you've got in terms of space for the existing positive conductor rail that sits in this place here, going through, what's my clearance to the render? So we need to provide 25 mm clear at all times. I may or may not be there, and therefore there'll be a secondary means of protection involved. If I put in a form of composite conductor rail, what does that do in terms of my clearance? So again, the whole power solution on what the power engineer models and therefore what they recommend to the track engineer in terms of the conductor rail that needs to be installed, and its own further challenges as you go through. And that's just some photos of some work that we've done. And as you can see there, some of the older forms makes it easier to put the conductor rail through. Sometimes we're doing track reconditioning works at the same time that we wanted to change the conductor rail to go through, which adds a little bit of a complication to it. Or we've decreed the works have taken place that's sufficient for what we're not going to be renewing the track for another 20 years, and therefore we can go out and install the conductor rail. Composite conductor rail expands more than steel conductor rail, so therefore you have to cut more expansion gaps into it to allow for that expansion. Each of those gaps will have cabling that runs round. So again, when you decide on where you think your gaps are going to be, one of the things that you have to check is there sufficient room to run the power cables around the gap, allowing for expansion of the conductor rails in traffic. The old steel conductor rail does get removed. We try to recycle where it can on other London Underground lines, but we are restricted for space at Rice Depot with how much we can hold, and then it tends to sort of be parted off and traded off against carbon credits, things like that. In terms of other track issues, I've touched on sight lines. This is an example of a typical sight line plot that you will have for sighting signals from the front cab, allowing for the different percentiles of driver that you allow for in terms of the 5th and 95% in terms of height and so on. And that sort of ends up describing where the optimum place is going to go. However, what we find is that you may have a signal here that has to stay there, but it's actually already infringing your structure profile. So you then end up saying to yourself, I can't move it longitudinally because the signal engineer tells me it's got to go there, safe operation of the drain. So what can I do? Can I go up? Normally. Can I go down? But of course, if I go down, I need to check can it still be seen or not? Or do I go in and can I nudge it across 30 mil to get the right clearance as I go through for these things? And often the type of clearances that we are dealing with is of that order. If you look over on here, from memory, I think this is Victoria, you can see where they've got a signal that's sitting in the 6 foot. The problem that you've got is one track is higher to another track. That creates issues in terms of sighting as you go through. And what we will also find is you can see this thing here that looks like a periscope. That's part of the CCTV system for the new trains. So again, that needs to be fitted somewhere on the infrastructure where we didn't have it before. So what was already congested, again, is my friend the catch pit, exactly where I don't want it. Signalling equipment needs to go where it needs to go. Tracks at different heights. Things are not quite as wide apart as they should be. And as you can imagine, in the station grounds, as much as I might want to move for the viewpoint of the signals, I'm also really interested in what's the relationship between the track and the platform because of maintaining the platform train interface. Moving on, this is an example of the sort of thing that we end up working our way through in terms of saying, okay, where's the new train? Where's the stop marks going to go? What type of signage do I have on the railway? It's the conductor rail the right length. Where's the signalling equipment? How does it all come together as we go through for these things? One of the things that we've had to look at as well is that with the change in new trains, the driver's cab extends further over the front axle compared to the old trains. That means that if the signalling engineer has been really tight for space for positioning their joints relative to the fouling points on different routes, that you can end up with a situation where the signalling system still works, but because the overhang is longer, the trains actually come closer together on the system that you go through for these things. So that's something that we had to work with when we were working through the rollout of S-blocking in particular. Wheel rail interface, I won't profess to say a great deal about wheel rail interface because there are others that could talk forever and a day about it. But it is an issue that we need to carefully manage because the trains will end up having a new wheel profile. The old rails are worn to the profile of the old stock, and therefore there's a transition period as you go through. And you have a series of problems anyway managing the wheel rail interface in terms of what you get through there. For instance, here, shortwave corrugation is an issue, RCF is an issue going through there, squats and so on through. What we've also found, just to make our life easier, is if you do a new fleet of trains and you put a new signalling system on, it's really difficult to get the wheel rail interface back together again. So this is an example of the north side of the circle where the rails were performing quite well. The white marks are T-pieces of insulated rail joints. For reasons I didn't agree with at the time, a decision was made to work with a 12mm T-piece. And it worked fine on legacy signalling still. When we went to the new signalling system, 12mm was just enough for the wheels of the train to get into the plastic under the signalling system control. And what you ended up with this deterioration of the railhead. That took about 3 months to develop. So it can happen very quickly, very rapidly, and you're then finding you've got new set of problems that you need to work with. In terms of track renewals, just sort of some examples of ballasted track renewals on either side as you go through. Again, some very different infrastructure. Some places, you've got more space. Typically, for ballasted track renewals, you'll use one road as a service road for taking your old track away, putting your new track back in again, as you can go through there. But there isn't masses of space. There's not the access points that you would necessarily want. The middle photograph is taken of a deep tube recon. Because it's difficult to get plant in there and other bits and pieces. We tend to rely on a lot of skilled labour. It's hot, dirty work. They may only work mostly 2.5 hours a night as they go through for these things. But as I say, it does get hot, creates no end of issues. And as you can see down there, it's really quite a difficult environment to work in logistically. So, when they say, for instance, oh yeah, can you just go and renew this piece of track? The deep tube tunnel, there's a lot more involved with it. So at the moment, we're looking at how we can maximise our production in those type of environments, but with current access in a deep tube tunnel, 350 metres takes about a year to do. And of course, you've got the issue about at the end of engineering hours, you have to check that the site is safe and back for trains and to make sure you don't overrun. So, the gangs that do it are skilled, and we desperately need to do something different.
Questions? Thank you very much. Anyone brave enough to take the blue box? Someone online? Graham?
Hi guys, sorry, I was just about to leave because I have to leave early, but since you come to questions, I might as well ask them physically while I'm here still. So there are two questions I've got for you, Andy. First of all, thanks for a brilliant presentation. It was really interesting. And I've got to say, I've met my mantra of trying to learn something new every day, and you've taught me a few new things on this one. But my questions are, two of them. Can you describe how the laser gauging system deals with gauge widening on curves when the laser gauge measurement is indexed to one side of the running rail, and the train could be going slowly and therefore leaning hard against the opposite inside face of the running rail?
Yeah.
How does gauging deal with that? And secondly, whenever we introduce a new train, there's nearly always a big dust disturbance. So again, could you introduce or could you describe how the track department sort of deal with the potential dust issues that can arise?
So, all right, okay. So the survey gauging one is the easier one of the two. So on the trolleys with the wheels that you saw, one wheel is fixed and the other wheels have springs against them. So they will push the wheel out so they're always in contact with the running face of the rail. So if you widen the gauge, the two wheels on springs effectively get pushed out. You always go to that position. Dust has been an issue, Graham, I would agree. It's a continual battle that we're fighting for these things. We've tried various bits of kit, as of like industrial hoovers, often just letting a train run through and do the dusting for us and clearing up afterwards is a way. Wouldn't recommend it's the best way. But no, we're not as good on that, Graham, as we should be.
I mean, I think we also do the odd polystyrene run, which also helps move the dust around as well occasionally when a new train's introduced.
Yeah, I've never realised rolling stock engineers like polystyrene for dusting tunnels, but there you are. Certainly doesn't work for gauging, Graham.
Certainly not, no. Anyway, thank you, Andrew.
Thank you, Graham.
Graham, I think Malcolm had a question.
Hello, Andrew.
Hello, Malcolm.
Like Graham, congratulations on a first-class presentation. And equally like Graham, every day is a learning day. I can confess that I was one of those who advocated the longer trains, so blame me. But having seen the photographs of the buffer stops, I'm overjoyed that they've all had to be replaced. But they were hardly arrestors. But real question is, have you managed to secure some reliable supply of composite conductor rail? Because I'd understood that Brecknell Willis have stopped production.
You are correct, Graham. We haven't yet managed to.
I'm Malcolm.
We are due to go out to the market. We have been contacted by two would-be suppliers. Undoubtedly through the tender process, there may be others. But it is a issue of concern for us at the moment of, how do we manage the interim situation as we need suppliers in place. But, I'm not alone in the railway industry with having suppliers that have suddenly decided we're going to stop making that and leaving us in a position. I know certainly from talking with Ian and other colleagues in rolling stock, the issues that they've got with their supply chain. So I don't take much consolation in it, but I know we've all got problems with our supply chains these days.
Thanks very much.
None in the room.
Thank you very much for your very interesting presentation. Is there any key learning you've had from other operators or other countries where there's been some major issues that they've kind of overlooked, and then with hindsight, it's become very difficult to rectify? So, for example, I think very recently for Glasgow subway, they introduced new rolling stock over the last few years or so, and I've heard that apparently they had to make modifications to the tunnels because the rolling stock wouldn't necessarily fit completely in that. Are you aware of any other examples that London Underground is able to be learned from this?
Yeah, no, we were aware of what was going on Merseyrail, and we were a little bit disappointed they didn't pick up the phone and talk to us, because we could have saved them time and money. Yeah, we do try to share knowledge and understanding through different forums, but again, it depends on the railway. You know, a number of railways, like take the age of Hong Kong and Singapore, they're only getting to the stage now where they're looking to replace things, or if they do replace trains, they're almost like a carbon copy of the previous one. And therefore you don't necessarily have the discussion that's involved in doing these things. And possibly we're at fault as well, we don't advertise enough of what we do. So, yeah.
What's best control?
You can. Yeah, thanks, Andrew. Great presentation. I was really interested by the gapping issues. I think I did a few gapping studies when I in my time when it was in graduate scheme, or just off it. And I suddenly thought about the 24 tube stock, and that is that going to be a complete nightmare in terms of gapping, given it's quite a different architecture that we're used to with articulated vehicles on single bogies.
Yeah, from a gapping perspective, actually 24 tube stocks make my life easier. Because it has its own internal batteries that it gives it its own ability to move under the power of those batteries. Now, quite how that will translate through into an operational environment, I don't know. But at the moment, with our level of understanding, gapping is a lot easier for 24 tube stock.
Okay, that sounds like a win.
Yeah, it is. Oh, great, I'll take that every day.
Jeez. Yeah. No, I'll ask one more then. In terms of that, was it Baker Street you were showing? That was certainly the one that we heard a little bit about.
I'll give you a prize after.
What was that? I was curious. I knew there was a problem. I heard about that, but I don't know what the solution was, which you alluded to post the old stock being removed. Were you able to move the track over a little bit or something like that? Or
no, we're actually gearing up for a new phase of a project where we're going to end up moving the train 30 metres north.
Right, okay.
It's quite expensive because of the modifications to the platforms that are there, but it will greatly reduce the number of doors where we've got an excessive gap, which is an issue at Baker Street.
Okay, thank you. Any more from anyone?
Thank you. Andrew, can you comment on stress-free temperatures in the running rails and the conductor rails? So if part of the underground for the London Underground, the central part, which is made mostly underground, and the outsides that are above ground, maybe if it's a separate lecture or something, with regards to the management of stress-free temperatures here on the inside and then on the outside, and is it the same, or if it's also applicable to the conductor rails? Thank you.
So historically, we've always managed expansion of running rails differently to conductor rail. The deep tube tunnels, yes, you don't get the tunnel variation. The heat variation in the tunnels as a general rule. Although, we are aware from the viewpoint of the travelling public, which includes myself, that tube trains can often be quite hot, particularly during the summer. So that is an issue. But generally speaking, we tend to look at overall expansion of the conductor rail as opposed to what's its actual stress-free temperature. But within the design of the conductor rail, we have means of checking the growth of the conductor rail with heat. With what they refer to as anchors, whether it's bit attached to the rail foot that increase the drag Obviously, the insulator system is not designed to retain the conductor rail. It's designed to work with the conductor rail. Running rail on the tube is a lot easier to deal with. Generally speaking, we don't worry about expansion gaps. Subsurface railway is an absolute nightmare to stress because it's not a continuous tunnel that you're in. You've actually got pockets of openings as well as other areas where effectively it sits in, between walls. And therefore you get certain times of the day where the rails get exposure depending on what the buildings are. Buildings in London have a habit of coming down and going up again in a different place, different height, which makes life interesting. Generally speaking, though, the stress-free temperature for running rails in the subsurface is easier to manage than in the open areas. We have been discussing the management of FST for Transport for London in light of the recent hot summers. I was quite pleased. Touch wood, may it continue. We didn't have any buckling during the very high hot temperatures a couple of years ago. That obviously says our standard is where it should be. What we're looking to do is to say, what improvements can we get? Because unlike the mainline railway, we're far more geographically located, so we don't have to worry about having a standard that deals with the temperatures in Cornwall or the temperatures in the north of Scotland. It's far more localised for that. Key part of that going forward will be how we monitor rail temperature, particularly during daylight hours. So, we find the current rule set works relatively well for us, but I think we can do better, and we will continue to look at how we manage stress-free temperature of running rails.
Thank you.
Thank you.
Yeah. Did you find a more suitable place for the plant pots after the upgrades to the arrestors?
I don't know yet. Waiting to find out. I think we probably did find something for them. Yeah, and again, credit to the operational staff. They do some really great things with stations in bloom. And it lifts our spirits when we see some of the things they get up to, as well as it must do for the travelling public. So I guess they will repurpose.
Any other questions? Oh, we'll leave it there. Thank you. From my perspective, really interesting. I've done some new train introductions on the main line, on the rolling stock side, and it's fascinating to see it from the other aspect, I think, and also an integrated railway. It makes I think it makes a lot of things more straightforward. It probably makes some things more difficult. It makes some things, to be honest, there's some things that we, in the projects I've worked on, never even touched on, didn't even think about, perhaps got away with, perhaps became a problem later on down the line, I don't know. But really interesting to see that sort of, that holistic approach that's been taken there. So thank you very much.